right, this is Chapter 8, the Periodic Table in Atoms. This is the last lecture, Lecture 7. And you might be going, wait, I saw that slide before. Why is it back? Well, this is actually related to the periodic table. So remember when we were looking at this, we were looking at the shell model and the Bohr model. And we saw that shell 1 has 2 electrons, shells 2 and 3 have 8 electrons, shells 4 and 5 have 18 electrons each, and shells 6 and 7 have 32 electrons. And if you take a second and think about that, there are how many shells? 7. And we just got done looking at the periodic table. And what does the periodic table have 7 of? It has 7 periods. So let's take a look at that. So here we've got our little periodic table. It doesn't have all the elements in it. It's just so we can see the general pattern. And that's the thing. The shell model actually accounts for the periodic table, the periods on the periodic table. So if we look, why are there only 2 elements in period 1? I mean, that's why we've got the little peaks up here on the castle. So this is hydrogen and helium, hydrogen and helium. So why are there only 2 elements in period 1? Well, that's the first shell. If we take a look down here at our little diagrams, and how many electrons can the first shell hold? It can only hold 2. So since the first shell can only hold 2, we can only have 2 elements that are in that group as far as the period goes. So that's why we've only got 2 in the first period. So second shell, how many electrons can the second shell hold? It can hold 8. How many elements are in the second period? Well, 1, 2, 3, 4, 5, 6, 7, 8. I know, right? It's crazy. And then if you go to the third shell and the third period, again, third shell has, oh, I didn't want that to come up yet. Third shell has 8 available electrons, and there are 8 elements in the third period. If you count them across here, I can guarantee you there are 18 elements because this is the 4th shell and the 5th shell, so there's 18. And then if you go to the 6th shell or the 6th period, how many would be there? 32. Now we don't have the 7th one completely full because there are the ones over here we haven't discovered, but that's how we can estimate what those elements might look like because we know what their numbers, their atomic numbers would be, and what their properties might be, since we know what families they would be in based on what we see also with the other elements that are in that same period. So that explains the periods on the table. Now let's take a look at the groups. And we saw that the groups have very common things in common as far as their properties, and that has to do with their electrons. So if we look again, it's a lot easier to see now that we've got nice drawings instead of my strange drawings. But you can see our first period, or our first group elements, hydrogen, lithium, sodium. What do we notice about these elements? They all have 1 electron in their outermost shell, right? So all of the other shells are full. If we could keep going, if we had this drawn out going farther down, then you'd be able to see that with the next ones down. You can see that too with group 2. We start with beryllium. It's got 2 in its second shell. We've got magnesium with 2 in its third shell. We can scoot across to group 3. We've got 3 in the outer shell here, 3 in the outer shell here, all the way across until we get to the noble gases, to group 8. Now, helium, it's not going to have 8 in its outermost shell. It's not going to have that full shell as far as 8, but it will have 2 because it's got just those 2. And so that's considered full. If we go down to neon, it's going to have 8. and argon will have 8, and so on down the group. So this is actually why the periodic table ends up being this shape, because of the shells going this direction on the periods, and then the electrons in those outermost shells going in the columns. And this pattern actually showed up before we really understood all of these properties, as far as the electron shells and things like that. Because they were put together in these groups based on their common properties. So then the next thing to look at before we get into chapter 9 is, how do we represent those outer orbital electrons? How do we represent what we will see later too are called valence electrons, the outermost electrons that are in that outermost layer? So we use electron dot diagrams. That way we don't have to draw all of the different shells. We only have to draw the outermost one. And so now we can see all of the groups for the whole column. And you can see that that pattern is the same all the way down. One outer electron for the whole alkali group, 2 outer electrons for the whole alkali earth group, and across. Now, this textbook has drawn the electron dot diagrams in this manner so that they've got them paired. You'll actually see when I start drawing these that I draw them a little differently, so it's up to you on how you want to use them, because they've got these drawn in pairs. The thing is that these electrons are actually not going to act as pairs, so very often what I will end up doing, like for something like beryllium, I will actually draw beryllium like this and put 1 electron on this side and 1 electron on this side so that I know that those 2 electrons are available. For carbon, for example, they've got these guys all drawn this way. Most books that I've worked out of actually draw carbon like this. So they've got 1 here, 1 here, 1 here, and 1 here. Because all 4 of those electrons are available to basically bond with other elements. So those are the electron dot diagrams, and you'll see more of those when we get into the next chapter talking about bonds. The last thing that I want to talk about with this chapter is ions. That way we can talk about it now, and then we'll be using this when we get to chapter 9, talking about how we bond atoms together. So ions, these are elements other than the noble gases that can gain or lose electrons to get a filled outer electron shell. So there are a few elements that tend not to do this, to not become ions. Things like carbon, the whole group that carbon is in, they tend not to do to create ions, but the alkali metals, the alkali earth metals, the chalagens and halogens, they all tend to do this gain or loss of electrons. So you can see here we've got lithium and fluorine as our 2 examples. And this, what happens is when they gain or lose electrons, that actually unbalances the charges, and that's why we call them electrons, to show that they have those unbalanced charges versus being a neutral atom. So let's take a look at what's happened. So when they do become an ion, we've got lithium. We saw lithium earlier. It's got a atomic number of 3, and so that means it's got 3 protons, 3 electrons if it's neutral. Now lithium has this 1 electron in its outer orbital, in its outermost electron shell. And the thing is that atoms don't like having basically missing electrons, or, well, extra electrons, if you want to think of it this way. So they have 1 electron here, and what they want is 8. And so this one electron is causing problems. They either need to get rid of it or gain 7. It's easier, if you think about it that way, to get rid of it. So they, in something like lithium, are going to get rid of that electron, give it away, lose it to someone else. And so here we get lithium as its ion. It's got a positive 3 charge. It's got its 3 protons. It's now got its 2 electrons in a filled shell. And because we've got 3 protons and 2 electrons, that means that we have a +1 or positive lithium ion. And so this would be a positive lithium. Sometimes you'll just see it written like this, lithium positive. Sometimes you may see it written as Li plus 1. It's rare to see them written this way because when we only have a charge of 1 as the difference, we just assume that it's a 1 and we put the positive or the negative. So down here we've got the opposite going on. We have fluorine. Fluorine has 7 electrons in its outermost orbital or outermost electron shell. And again, it wants it to be full or it wants to drop down to the next one that's full. So here it's got 7, so it only needs 1. And so it's going to get 1 from somewhere, say a lithium. So it's going to add an electron to that shell so that now we have a total of 8 in that shell. But what that does is fluorine, as you can see, it's got 9 protons. It has an atomic number of 9. So by doing that, when it gains that electron, it gets 10 electrons. And so 9 protons and 10 electrons means that we have 1 extra electron or a negative charge on this atom. And so we get a negative fluorine. If we were to do this with something like calcium, calcium is like lithium, but it has 2 electrons out here. So when it gets rid of it, it's going to be a calcium 2+, or you might see it written +2. You see it written both directions. So Ca +2. So you can see it written either direction, but that would mean the same thing as far as the ion. So who tends to become which type? Metals tend to lose electrons, so that means they're going to become positive ions like lithium. So any of the metals, like I said, alkali and alkali earth metals tend to become ions. So any of those guys from the left-hand side, we also get transition metals that will become ions. Non-metals tend to gain electrons. So if it's a non-metal and it's going to become an ion, then it's going to become a negative ion because they're going to gain electrons to fill that shell, and so they'll become a negative ion. So let's just do a little bit of practice. So get out your periodic table if you don't have it out, and let's take a look what type of ion which each of the following elements become. So the first one is potassium. So find potassium on your periodic table and figure out what type of ion that would become. So let's look. So potassium is right here. It's in group 1A. That means it has 1 outer electron. So it's going to actually act just like lithium. So it's going to be K positive, right? It's going to have a positive 1 charge. So I'll put these other ones up and you can take a look at them. So try sulfur and iodine and see if you can find what the ions would be for those elements. And with that, oh wait, sorry, I forgot. I have one more, barium. And with that, that is the end of Chapter 8. chapter 9, we are going to start talking about how to put these atoms together.